generally not the happy time for people because you're filled with stress like, did I do a good job? Did I do a bad job? So one thing before I get them graded you can do is look at what the solutions were and then kind of at least say, oh, yeah, I knew that one, hopefully. So to find the solutions in the Chapter 3 section, I have the solutions. So, for instance, if you are in the class here at Union College, or if you are in the 2 p.m. lab section over there at Southwestern, then you had the exam 1A. So you can click there for the solution. It'll bring up the PDF file with my overkill solutions here. So you can see my explanations for the problems and get a better gauge before they're graded on how you actually did. So that's a resource there for you to look at. Are there any questions about the exam before I start lecturing? Okay, I see. Okay, I'm going to take this as a no, I didn't see any hands here or there. So back to, oh, okay, there's a question in Southwestern.
You want me to put the solution out for 1A? What about 1B?
No, 1B was right below it. Here, let me show you. So for the people in the evening class, it's 1B right there below it.
Thank you.
Yeah. Okay. So we're back to, obviously I reused this. I don't know when Harvey's Harvest may or may not be reset to. They reneged on their we're still going to do it thing. So, do it, but in the atrium. But we're back to talking about forces. So start with, oh goodness, I only got halfway through setting this up. So you can't answer yet, but you can read the question and be ready to answer when it comes up. I knew I was something short here. This is a question we had on Friday, and I'm asking it again because, well, we forget a lot of things from Friday to the next Wednesday, especially when you've been studying for an exam. Only you could see how slow I am at opening files. Okay, you can answer now. And yes, answers should come flying in here because you had plenty of lead time to read and to get everything set up. So I'll just give it about another 10 seconds here because it should be all punched in. Yes, sir. What'd you say?
I can't connect to the.
It's working because people at Southwestern are being able to. Okay. There should be more for you to catch up because you only have to answer 60%. So I'm going to stop it here. We had 46 responses. 4, 1, 0, 31, and 10. So you can see that there was a majority here. It's always good, but still not perfectly clear. And so a reminder of what a free body diagram is and then its importance. Free body diagram is a diagram that shows all the forces acting on the object you're interested in. The reason we do that, now that's not all the forces in the problem. It's all the forces on the object we're interested in. The reason we do it is primarily so we can easily apply Newton's second law. But as we said on Friday, that's not the only reason. There are other correct answers. And another good answer is so we don't forget a force. So we have a way of looking and saying, yeah, I got them all there. Another one that for a student actually makes sense is, so we can show the teacher that we know what's going on. I mean, that's what a test is all about, remember? When you take that test, that's your time to show me that you're the master, that you've got this stuff. And I hope when I'm grading to see lots of people who are showing me that they really understand this, because, of course, my goal is for everyone to understand the material. The Newton's third law, a free body diagram does not show the Newton's third law reaction forces. It only shows the forces on an object, not the forces it puts on other things. So this would have been a wrong answer here, because it specifically does not show the Newton's third law reaction forces. Okay, now let's look at, we've already looked at some of the forces. Just a very quick reminder, gravity is a force that's always attractive. This is the universal law of gravitation equation. Notice that's written not as a vector equation, but as a scalar equation. Gravity, like all forces, is a vector, and its direction is always going to be in the direction toward the other object. So if we were to take, as an example, the force between me and the video camera, I am pulling the video camera toward me. That's the direction of the force of gravity that I'm applying to the camera. The camera is pulling me toward it. And so you look at the object and you say the gravity is attracting it to the other object. As long as we're on the surface of the Earth, we abbreviate the force by saying that it's equal to mg, where m is the mass of the object I'm looking at, g is the acceleration of gravity. That's just taking this equation and applying it where the distance between the center of the Earth and the object is the radius of the Earth, and the mass of the other object is the mass of the Earth. So g is just calculated by taking those numbers from this equation here. And we talked about that on Friday. The normal force we talked about, it's simply the force to keep stuff from falling through a surface, right? The surface doesn't open up and things fall through, so it's a force that's pushing things outward. So its direction is the normal direction, the direction pointing out of a surface, and it will have whatever value is necessary to keep the thing from going into the surface. Unless, of course, you put more than the ultimate strength of that surface, in which case the surface breaks. Normal force is a contact force, so when I'm playing around throwing a ball, if it's in the air and not touching anything, there's no normal force on it. But when it's sitting on the corner of the desk, then there's a normal force keeping it from falling through the desk. So it's contact force. Now we're going to get into these other forces and along the way solve some problems. So while I have spring listed next there, it's not the next thing. A picture we've already seen of a snow skier. Look, Richard Henriquez joined our video call. Hey, Richard. So we have this snow skier going down a hill. This picture illustrates a couple things. I'm going to do a simplified version of solving for the acceleration of the snow skier in a moment. But a first thing to note is the forces are shown in this picture here. We have the forces that are acting on the snow skier shown acting on the snow skier. Over here we have a diagram that is the technically correct free body diagram. And you might recall from Friday, I said I'm very happy for you to just have the picture on the left. If you have all the forces that are acting on the object you're interested in, which in this case is the snow skier, on that diagram and no other forces to deceive you, then that's fine. If you have other forces, if you had forces like, well, the force of him pushing on the ground, then you would have to have a separate one for the free body diagram so you don't have more forces than you should have. I'm going to erase these annoying squares. So that's the first thing. The second thing, and this one I haven't spoken about at all, is the two coordinate directions that were chosen. You can see this figure shows a suggested set of coordinates that are marked as parallel and perpendicular. Parallel is what these two parallel lines mean. Perpendicular is what that means. So that's not what we've been using up to this point for our directions? What have you been using for our directions up to this point?
Up, down, and cardinal.
Okay, things like vertical and horizontal, right? If we had an x-axis and a y-axis, we made the x-axis horizontal, the y-axis vertical. Well, that's not what was done here. And so there's a good reason that it's done this way. And if you understand the reason, it makes it a lot easier in the future to choose your axes. So we learned that motion in the two perpendicular directions is independent. And so we've just finished solving problems on tests where we had acceleration in the vertical direction and no acceleration in the horizontal direction. So we chose our directions, vertical and horizontal. Why choose those? Because no horizontal acceleration makes it really easy to solve your horizontal part of the problem. Only the vertical one has the time squared. The general rule for deciding what you're going to use for your axes is number one, align. That's not how you spell one. One, thinking about the Raiders, one on Sunday, you know. One coordinate system or direction to be parallel to acceleration. Now, acceleration, you only have one direction for acceleration. So you choose one coordinate to be parallel to acceleration so that the other one's perpendicular and has no acceleration in that direction. So in this picture, the skier is moving with a changing velocity down the slope, hence accelerating down the slope. So down the slope is the direction of the acceleration. What's the skier's speed parallel to the component of his velocity in that perpendicular direction? How quickly is he moving in the perpendicular direction as shown here? He's not. If he's not moving and he remains not moving in that direction, that means he's not accelerating. If he was moving at constant speed in that direction, it would still be not accelerating. We sometimes forget and say, oh, has to be not moving in that direction to have no acceleration. But he's not accelerating in the perpendicular direction, only in the parallel. Now, there is a second thing to this coordinate choice that may seem uncomfortable to most people. We have the positive direction for the parallel is going up the slope. Well, what direction is he accelerating? Down the slope. And a lot of times people are going to say, well, I want my acceleration to be parallel, not anti-parallel. After all, I did say parallel in what I wrote. Well, there's a second thing. We want to keep our coordinate system a right-hand coordinate system. And I'm guessing almost everyone has no idea what that means. The second one is purely a convention. That means you don't have to follow it. It's just a standard. A right-hand coordinate system is where x cross y equals z. If you haven't studied cross products, that's okay because that's part of algebra and it's part of algebra we use in physics, so I'll be teaching you them later. But basically, you need to have a counterclockwise going from x to y, counterclockwise 9 degrees going from x to y for right-hand coordinate system. And so that's why it has plus going up the slope. So you have those two rules. A final rule is, if you didn't have number one, set a direction, choose the easiest set. So follow those priorities. If there's an acceleration, align your coordinates so one coordinate is parallel to the acceleration. Use a right-hand coordinate system. It's a convention. You don't have to. Choose the easiest directions if you don't have acceleration. So if you don't have acceleration, just think about what's easy to you. Do you have a question back there, Cody?
Could you flip the diagram around and then say he's going downhill?
I often do things like that. I'll make a picture where he's skiing down a slope like this. And then my x is going down slope and the acceleration is in the positive direction. That's what you were asking, right, Cody?
Yeah.
Yeah. So he asked if you can flip the diagram around. That's often what I do. Of course, I do that when I'm making a problem. And I didn't make this problem. It was from the textbook. Okay, second thing on this, breaking our forces into components. Now, we've already been breaking velocity vectors into components. We had to do that on the test yesterday. Doing forces, we're going to have to break it into components, one parallel to one axis, one parallel to the other. We call a problem like this skier an inclined plane problem because he's on a flat plane that is inclined with respect to the horizontal. So for this inclined plane, I need to break, in this case, the force of gravity vector into the part that is parallel to the slope and the part that's perpendicular to the slope. So we have an angle that's given right here, and we need to figure out how that relates. So my process of breaking the force vector into components is actually really quite simple. I start by drawing that force vector line. So instead of using the one that is already solved, I'll just do another one. That was almost, but not quite, straight down. Okay, that's as close as I can get to straight down. And so there's my force of gravity equals mg. I put right away force of gravity equals mg, so when I'm doing my work, I'll have that mg, which is generally more telling to me. Then I will make lines starting at each end of my force vector, one parallel to the x direction, shall we say, one parallel to the y. This here is, I mean, you can kind of choose which one you want, but following the norm, there's my y direction. So that dashed line is a line parallel to the y-axis that goes through one side of my force vector. Then I'm going to make a line parallel to the x-axis that goes through the other end of my force vector. So there we have the x and y laid out with my force vector. The components are the pieces, the little vectors that when added up give me my total vector. So that means my component has to start here and end up here. And to do that, I go down and then left. So now I can see my two components. This is the force of gravity y component. This is the force of gravity x component. That's a right angle because I have right angles between my coordinate directions. And the last thing I need is to know one of the angles in this triangle. And knowing the angles in the triangle, okay, I've done this since I was, 18-ish. Well, 17, that's when I started college. Turned 18, first quarter. So I've been doing this a long time. And so I just look at this and I know, but you guys haven't. So you have to find a way of identifying, okay, I know this angle between horizontal and the incline. How do I put that into this triangle here that I just made that has one side is parallel to the incline and one side is perpendicular to the incline? Here is the way that I always remember. This direction here is perpendicular to that. That was really awesome. This direction is perpendicular to that one. So my y is perpendicular to the incline. And then my force is perpendicular to the bottom. And so with those perpendiculars, the angle between two perpendiculars has to be the same as the angle between the two they're based on. So this line here is perpendicular to this one, and this line here is perpendicular to this one. So the angle between those two has to be the same as the angle between the ones I marked 1 and 2. That's how I remember it. Here's another way that might work better for you. Just imagine making the slope smaller and smaller and smaller. Which angle is getting smaller in this? Undo. Change the thing to erase. Which angle is getting smaller here as I make my incline flatter and flatter? That's got to be the one that's my elevation angle. So that one you can just think about it logically. Okay, so it's like at an angle, if I flatten it out, which would be getting smaller. So after doing all of that, we determined that this angle here is the same angle as that incline angle. One more misstep that I know I have made in the past. I have done this where I made my right angle here and went like this. That's not right. It's not right because that blue line is not parallel to one of my coordinate directions. Am I standing in the way? I know students at Southwestern can't see, but I have students leaning over sideways to try to see the screen. I have now a wired internet connection, so we should not lose the internet connection this time. So that blue one is not the right. I'm just going to undo out all of those dashes for the blue because it's not parallel to one of my component directions. If you try to use that one, you're going to get wrong answers and you'll wonder, what did I do wrong? And it came down to your components. Okay, now that we have a triangle, now it's just trigonometry. I have my force Gx is the opposite side. My force Gy is the adjacent side. So that means just using my trigonometric functions, which they're shown there, but I will have cosine of theta is adjacent over hypotenuse. So adjacent to this blue angle is force Gy. And then the hypotenuse was mg. So that gives me right away force G in the y direction is equal to mg cosine theta. And then do the same thing for the opposite for sine theta is equal to the opposite side, fgx over mg. So therefore, fgx is equal to mg sine theta. I just looked at the solutions that are written here and I got my parallel and perpendicular confused and thought, oh no, what did I do wrong? No, I did it right. Those are the magnitudes of the forces. My actual arrows tell me the directions. So if I look at my directions, is FGY positive or negative? It's negative because this arrow on my component is pointing the opposite direction of the arrow that defined the y direction. So my FGY is going to be actually minus mg. Mgy was cosine, or force Gy was cosine. And then my FGX, is this x component parallel or anti-parallel? Anti-parallel means 180 degrees opposite to the x direction. It's anti-parallel, so that one also is negative. So there I've broken my force of gravity vector into my two component directions. Now I think I have a problem here before I go further. We have the snow skier going straight down an incline of 25 degrees. If the friction and wind resistance are negligible, what is his acceleration? So we've just done this. We've broken everything up. So I now know that I'm going to have, for a free body diagram, I have the force of gravity. Nice equal sign there. That we broke up into components. What other forces are going to be acting on the snow skier? They were on the previous diagram, but I want to make sure we can name them.
Normal force.
Okay, normal force. If the slope is like this, the force normal is always perpendicular to that slope. So there's my force normal. How strong is the force normal? It's not a definite answer. It's however strong it needs to be to keep him from sinking into the hill. And I said that all the other forces are negligible. That is no air resistance, no friction. So I just have those forces. We have our coordinates that we've already set up. We break things into components. So I'm going to have my x component, my y components. And I'm going to put my forces here. So I'm going to list my forces. So I'm going to have, I write this in a redundant manner. Force of gravity equals how much in the x component direction, and then I'll put an x hat at the end. It's redundant because I have x as a column heading, and then I have in the x direction. But I want to read correctly as I read across horizontally. And likewise, I'll have how much in the y direction. So if I look at the force gravity, we broke it up in the previous page, and we determined that it was minus mg, I didn't give myself enough space, sine theta. Okay. Got to move it. Oh, finger came off the button. Got to move this over. In the x direction, and minus mg cosine theta in the y direction. So if you read this across horizontally, it says the force of gravity vector is minus mg sine theta in the x direction, minus mg cosine theta in the y direction. So that's one of the two force vectors. The other force vector is the force normal. So how much is force normal pointing in this x direction? None. None is the proper answer. It is simply not, so I'm going to have 0 in the x direction. How much is it pointing in the y direction? The answer, you don't have a number for it, it's just all. And so I'm going to put here plus force normal in the y direction. Now notice the vector sign here. Force normal vector is equal to 0 in the x direction plus force normal magnitude in the y direction. How do I differentiate vector versus magnitude? It's that arrow. So those are all the forces. Yeah, it's not the right. That one. Now I'm going to take this and I'm going to apply Newton's second law in each of the component directions. So I'm going to do, whoops. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. Sum of the forces in the y direction is equal to mass times acceleration in the y direction. You can tell me about one of the two accelerations. Which acceleration do we know? We know one of the accelerations exactly.
Gravity.
Not gravity. We do know gravity is an acceleration of the problem, but not ax or ay. So which one of those do I know exactly? I know that the acceleration in the y direction is 0. How do I know that? Because I chose my coordinate directions. So the acceleration in the y direction is 0. So I'm going to do the y side first. Now for this problem, we didn't need to do the y side, but I'm going to do it anyway. So I look at my picture, or not my picture, but my breakdown of the components. And I say, okay, just adding up the things in the y direction. I always put the positive first. So I'll have force normal minus mg cosine theta. That's sum of the forces, just adding up the things in the column above, equals, and the acceleration in the y direction is 0, so I just put equals 0 because acceleration in the y direction is 0. Well, that right away allows me to solve for the force normal. That allows me to say force normal is equal to mg cosine theta. Now, if there had been another force acting in the y direction, that would have come into this equation, and force normal would not have been mg cosine theta. But if there's no other forces, that's what comes out. So I did the y direction. I found force normal was mg cosine theta. Now I go to the x direction, and adding up the things in that column, I'm going to have minus mg sine theta equals max. Well, what I asked you to find was the acceleration, ax. So divide by m, right? Divide both sides by m. And notice what happens on the left-hand side. The mass cancels. The mass canceled on both sides. And I have ax is equal to minus g sine theta, which is exactly what was going on with our lab with the inclined slope, where we had the carts rolling down the slope, the lab we did a week ago. The acceleration was down the slope. The minus sign is just for direction. G multiplied by the sine of the angle. So if the angle was 0, sine of 0 is 0, and it would have been 0 acceleration. If it was 90 degrees, then you would have had sine of 90 degrees is 1. The acceleration would have been g downward. And somewhere in between, well, it comes from the angle. So here we've solved what was asked for. And it was important to note, mass didn't matter here. The mass canceled out. It doesn't matter if we ignore air resistance. The mass simply doesn't matter. If we don't ignore air resistance, then the mass will make a difference. Which is why back when I was at PUC, I was racing a student. The student was like this tall, probably 140 pounds. I was toasting him. I was so far ahead. Unfortunately, at the bottom of the slope, there's just this little rolling thing. I went like this, crashed harshly, crawled back up and got my skis on before he caught up to me. But he ended up winning the race because I wasn't moving when he passed me. So having a big mass helps when there's air resistance involved, especially if you tuck, which back then I could tuck. Now, I don't know, I'm not so flexible. Okay, so our second clicker question, this is now going to reality rather than my contrived problem. What forces are acting on a snow skier in real life? And yes, this is one where you answer all that you find correct and then press enter, because there's obviously more than one force involved here. Yeah.
In real life or according to?
This is in real life. Okay. Closing it up here. Still have the same. I don't have an answer from you, Mahala. Okay. Other people, just for the people Southwest that I don't have an answer from. I don't have an answer from Crystal or Elizabeth or Jasleen or Gabriella. Okay, moving on. The answers we got here, 51 people said that there's weight involved. 49 people said there's a normal force. 3 said tension. 3 said a spring. 50 said friction. 49 said air resistance, and 34 said buoyancy / lift / fluid pressure. Now, we haven't talked about all of these, but we've done a good job of answering the question nonetheless. Is weight involved? Yes. All but one person agreed. The person who's skiing has a weight, and that's going to affect the skiing. Is there a normal force? Yes. The person is not falling through the slope. Now, they did sink some into that snow, but they didn't fall through it. So there's a normal force that's pushing outward to keep them from falling through the slope. There's a force of gravity downward. Tension. There are internal forces in the body that are tension. So if somebody wanted to argue this with me, I'd say, yes, there are internal forces in the body that are tension forces. Or there's, forces in the ski that are tension forces. But when we talk about the force act on the snow skier, we generally say, no, it's not acting on, it's acting within. Spring, likewise, acting within. Friction, well, yes, in real life, there is friction. That's why we wax the board, so we have less friction. Air resistance, yeah. I don't know if you guys have tried to ski fast, but if you're in a tuck, you can go a lot faster than if you're standing up. After that crash, the next year I tried to race the same guy, and every time I got going fast, I got scared and I stood up. And I noticeably slowed down, and then I'd be like angry at myself, tuck, get scared, stand up. It changes your speed a lot, that air resistance. The buoyancy lift fluid pressure one is very small because air has a small density. But basically, you know how you throw this ball into the water and it floats? It floats because of the pressure in the water increasing with depth. The pressure in the air also increases as you go down, and so that causes a small upward force. So there is a really, really tiny buoyancy force that's affecting all of us, but we ignore it uniformly if it's in air. The only time we don't ignore it is when we're talking about, well, hot air balloon. Mr. Meckel.
Right. Also, if the guy were to jump a hill or something like that, then there would be some lift acting on him, right?
Conceivably, there could be a little.
Okay.
And we will talk about these forces later on this semester, very much later on this semester. But those last ones are not ones that are going to be ones we're discussing in this chapter for the most part. They'll be assumed to be zero. Okay, spring force. I got 13 minutes. I want to do my demonstration, so let's do a little quickly. A spring force is a force that acts in a specific type of object, something that shows elastic behavior. Elastic means you deform it and it comes back when you let go. So, you got the elastic waistband in your coach's pants. You can pull them out, you let go, and it comes right back. That's what elasticity means. And if something is behaving elastically, then the actual amount that it stretches is proportional to the force. So if you make a bigger force, it stretches a bigger amount, and it's linear with force. So the equation to relate the force from a spring with how much you stretch it, so delta x is the stretch of the spring, is just dependent on a constant k, a constant. It's linearly dependent on how much you stretch it. Double the length of the string or spring, you have it stretched 5 centimeters, double that stretch 10 centimeters. You double the force that it's pulling to try to close it back up. The minus sign means that it's restoring. The force applied by a spring is going to be a force to try to bring it back into its neutral position, the position it would have if you weren't applying a force. And we will use a spring gauge for force when we do the demonstration. Next up, force of friction. Friction is an easy to misunderstand force. It's ubiquitous. It's everywhere. Without friction, we would be in trouble. Friction is a force that acts between two surfaces, and it depends on the types of materials that are present. So you have, as the picture shows, a surface that's rough. Any surface, if you look at it microscopically, you're going to have some roughness. And there are two things that go into the friction force to make it what it is. One is conformity. That is, if you take, for instance, the hands of my left hand, the hands of my fingers of my right hand, put them together, I can make them so they kind of conform, and so they don't slide past each other. And if I want to make them slide past each other, I have to push hard enough to make it rise up. So that's part of what causes the friction force, is a conformity between surfaces. Once you have it sliding, that conformity is not going to be as much of a problem because you've already lifted it up and you just keep it lifted as it slides across. The other one is actually interactions between atoms and molecules. we tend to think, okay, I have this stapler, one piece of material. I have this desk, another piece of material, that the atoms in the stapler and the atoms in the desk really aren't going to interact. For the most part, it's true, but it's not perfectly true. There are forces attracting them. You get close enough and they can actually be big enough that they will make it so it doesn't slide easily. So you have those two things that go together to give you the frictional force. Now that one, it does depend on distance. So if you get separated, that's going to also lower a little bit. So those two things come together to give us two ways we talk about friction. We talk about static friction. That's friction between two surfaces. The friction between two surfaces that are not moving with respect to each other. Static because the two surfaces are stationary with respect to each other. In that case, you have the conformity that's definitely there. You're going to have things closer than they would be if it was sliding. And so that static friction is always greater than or equal to the friction when they're sliding. The second one we call kinetic friction because kinetic means in motion. So we have two kinds of friction. We have static friction and kinetic friction. And when I put these in, I put them in incorrectly. The less than or equal should be with static friction. The kinetic should be an equal sign. Boy, I don't know how to fix that. Here's what I'm going to do. I'm going to put it equal below and get rid of that. The kinetic friction is equal to mu sub k. Mu, that Greek letter mu, is in this case the coefficient of friction. The k means it's kinetic. So the coefficient of kinetic friction times the force normal. The static friction, it's less than or equal to a maximum value. Why less than or equal to a maximum value? Let's just imagine the case of having my stapler. If I push on the stapler a little bit, it doesn't slide because of static friction. If I push harder, it will start to slide. And so there's a point where I reach the maximum static friction before it slides. Anything less than that, the static friction is not going to make it move into my finger. It's just going to keep it from sliding. And so it's just going to balance whatever force is on it until it reaches its maximum. So that's why the static is less than or equal to its maximum value. Now in problems, we will usually ask things like, what is the acceleration when it just starts to slide, or what's the maximum force before it starts to slide? Things like that that tell you, okay, we're going to be working right at that limit. Because if you just say, stapler's saying here, Richard pushes with 5 newtons and it doesn't move, what is the coefficient of static friction? You can only calculate, well, it has to be greater than or equal to this value. You can't actually calculate it. Unless we give you words that say, and it, it's just on the point of sliding, then okay, we're at the maximum. So kinetic friction, that one, since it's sliding, that one's going to be always an equal sign there. What about directions? Static friction will be in whatever direction is necessary to keep the object from sliding. Kinetic friction will be in the direction opposite velocity. So those are our friction forces. Here's some coefficients of friction just to get an idea of them. We like to go, well, we don't like to, we do sometimes go ice skating. And of course, steel on ice, if you have static friction, is pretty big. If it's kinetic friction, that's really, really tiny. And of course, what's better than steel on ice? Steel on water on ice. And if if the ice is close to its freezing temperature, the metal usually will melt it. And actually research suggests that it's not the pressure that's melting, it's more the temperature of the blade that's melting the ice to give you the water layer. When you have that water layer, it slides much better. It's always used as an example of pressure causing melting in ice, and then actual research says that wasn't actually what was going on. Other things that I find fun: bone lubricated by synovial fluid. We don't want our bones to grind. I can tell you this from actual experience, right? Football injury, had to have a chromioplasty because my bone grew and it was grinding. That's bad. But God made us so that we have very low friction between the bones So they shouldn't naturally grind. So we shouldn't have bone deterioration from just, walking around and doing normal things. And you can see, why do we oil things in our cars? Because if you have steel on steel and you oil it, it drops the coefficient of friction by about a factor of 10, which means less wear and tear on engine parts with oil by a factor of 10. That's why we put oil in them. Okay, our third and I believe final clicker question, especially since I only have 5 minutes. How would walking be affected if there was no friction? So this is asking you to apply what we just learned about friction, not something I've talked about, an application of the physics. Okay, and I'll give it just another 5 seconds here because we only have 4 minutes left in the class and I've got to do my demonstration. So answers we got here were, it's not stopping. Excellent. 1, 0, 11, 38. So the bulk of people, and this is one I should have asked somebody, but once again, for time, I'm not going to. The bulk of people said we wouldn't be able to walk, and that's correct. Because when you walk, if you walk on ice, you learn right away things not to do. Or at least if you're intelligent, you learn right away things not to do. What should you not do when you're walking on ice?
Go to one point of contact.
Yeah, go to one point of contact. Okay, one point of contact, we don't have as good balance. So that's a pretty good rule. Of course, when you're walking, you do have to go to one point of contact generally. I mean, you pick up a foot. Yeah, shuffle works. Don't make sudden movements. That's a real biggie. When I walk, I tend to really push hard with my feet. And if I do that on ice, well, I'm going to be down in no time flat because I need that friction. If we had no friction at all, when I push back on the ground, what's the ground going to do in response? Well, when I push back, it's not going to push me forward like it normally does because there'd be no friction. It would still push me up, but it wouldn't push me forward. So when I push my foot back to move me forward, my foot would just go back freely and plop. We would never be able to move ourselves anywhere except for doing things like take a ball and throw the ball and use that to propel yourself. Yes. Okay. Go ahead and change it to the preset 5 and change the camera over there at Southwest to show the video feed here. Now we're going to talk about tension. Tension is a force that is transmitted through something like a cable. So here I have a string, and the string is going over a pulley hanging down, and I have a mass of 100 grams that's hanging from it. Now the way tension works is it's distributing a force. So if I have 100 grams, what's the weight of this if it's 100 grams in mass? Okay, so I'm going to have the force of gravity is equal to mg, which would be 100 grams times 9.80 meters per second squared. That's grams. That's not kilograms. The standard unit is kilograms. That's 0.1 kilograms. 0.1 times 9.8 is going to be 0.98. So this is 0.98 newtons. Is this accelerating? No. So the acceleration is equal to 0. That means there has to be a force that's balancing that's up. And that upward force is what we call the force of tension. And so how do I find the force of tension? I apply Newton's second law. Sum of the forces in the y direction equals ma, which is 0 in this case. So I have the force of tension minus the force of gravity equals 0. The force of tension must equal then the force of gravity, or 0.98 newtons. So I have a force of tension that's pulling up. The tension force is always parallel to the string in the direction it leaves. Now tension, the word tension is that force is distributed through the string. So when the string comes up to this pulley, the string leaves the pulley in two different directions. One direction is downward, so it's going to apply a force of tension downward. It also leaves the pulley to the side, so it's also going to apply a force of tension to the side. Those forces of tension are all equal to the same thing, so we actually call the force that's being distributed the tension. So the tension would be 0.98 newtons, and the force of tension applied anywhere that string touches something is going to be that tension, 0.98 newtons, in the direction that the string leaves. Now, I know I'm out of time, but I at least have to do this. Here I have another 100 grams, and I'm going to put that 100 grams right here. What do you predict will happen?
They're going to come to the same point.
Okay? I got some answers. I heard one clearly, Gabriel's. But the key is for people to think about what they think is going to happen.
necessarily happen.
Put it on here because we're scientists. We want to check and see. And it came down, and now there's some friction here, so it's not floating freely. But we have this as being pulled up and to the right by the string on one side, up and to the left by the string on the other side. So I have 0.98 newtons this direction, 0.98 newtons this direction. If I add those forces together, what are they going to add up to? Okay, they're vectors, right? When I add those vectors, this is not accelerating any direction. So the sum of the forces in the horizontal direction is going to have to be 0. So the component of this force that's horizontal and this force that's horizontal are going to have to add up to 0. In the vertical direction, I have 0.98 newtons down, so the vertical component is going to have to add up to 0.98 newtons up. But clearly I can hold more than 0.98 newtons here with my 0.9 newtons there. So for my last little thing, I'll just add another 40 grams on this. And you'll see when I put 40 grams, it goes down lower, so the strings are pulling more upward. And thus you still have the upward force balancing, but because they're pulling more upward, it's more than 0.98 newtons down. Okay, we're 2 minutes past time. Have a great day. I will try to get as much grading as I can done tomorrow, but no problem.